Welcome to SumLab. This is part 3 on the nature and behaviour of electrons. If you've been following this series, you'll notice that a huge amount of time has elapsed since part 2. The truth is that I have videoed this experiment a number of times and just not been happy with the footage I've obtained. The colours are spectacular when viewed in person and fade to vague blobs when recorded on anything but the best camera equipment, which I don't have. Maybe that's a good thing though. This is an experiment that you could and probably should do for yourself. With that in mind, I will finish with a series of slides that let you know how you can get the chemicals you need to do this. The procedure is not difficult, and it is very rewarding. Critically, we're able to observe a phenomenon that is caused by something happening at the subatomic level. We are seeing with the naked eye the effect of electrons repositioning themselves in atoms. That's pretty cool if you think about it. For the theoretical background of what's going on, you probably need to watch parts 1 and 2 first, but I will briefly summarize the points that are critical to this experiment. Number 1. Electrons in an atom are identified by 4 quantum numbers n, l, m, and s. These 4 numbers determine an electron's shell, subshell, orbital, and spin, its quantum state. Number 2. No 2 electrons can have the same set of quantum numbers. You can think of the 4 numbers as an address, and no 2 electrons can occupy the same address. This is known as the Pauli exclusion principle. Number 3, the quantum numbers, n in particular, but also l and m to a lesser extent, reflect the amount of energy that the electron has. Higher n means higher energy. The upshot is this. If an electron is given energy, it must transition to a higher energy quantum state. And it can only do this if that state is vacant. There is not already an electron with those particular 4 quantum numbers. Conversely, if an electron is to lose energy, then it must fall back to a lower energy quantum state. Again, this is only possible if that state is vacant. It is worth noting that higher energy states are not as stable as lower energy states, in the same way that high branches of a tree are less stable than the ground. Given the opportunity, electrons will tend to lose energy and fall back to their ground state. That's the summary. Now for some physics. You will have inferred from the way I've described these energy states that electrons must have very particular amount of energy. No intermediate energy states are allowable. Only certain discrete energy values are available. This is why they are called quantum numbers, and this field is called quantum physics. The energy is quantized, which means that it comes in discrete bundles with precise calculable value. So, if an electron falls from a higher energy state to a lower one, then it must give off a bundle of energy. And the way this happens is by giving off a photon of light. But not just any photon, the photon must have exactly the right amount of energy, corresponding to the energy drop of the electron. Enter the Planck-Einstein equation. This equation tells us that the energy of a photon is directly related to the frequency of the light emitted. The h in this equation is simply a proportionality constant, Planck's constant. If an electron falls from a high state to a lower one, a photon of light will be emitted, and the frequency of that light is specific to the particular energy drop that occurred. Our eyes observe photons with different frequencies as different colors. So, what happens in this experiment? We take a sample of an element, usually as a chloride salt, we give it some energy, and some of the electrons get excited to a higher energy state. When they fall back to their original state, they emit light of very specific colors, which we can observe. In this variation, boron does not form a chloride salt. It tends to make covalent bonds and form molecules. But by dissolving boric acid in methanol, we form some trimethyl borate, and it is in this form that the electrons can be excited to a higher energy state. You don't need exotic chemicals to see these colours. Burning metals will show the same thing, particularly if they've corroded a little bit. Heat is not the only way of exciting electrons. An electrical spark through a gas at near vacuum will do the trick as well. This principle is used for a wide range of light bulbs. Here I have bulbs of neon and argon. I light them up using a small Tesla coil, which is a bit simpler than building a circuit. It gets better than this. If you view the light through a diffraction grating, you will separate it into various colours to form a spectrum. A prism, or even the surface of a CD, will do the same thing. With normal white light, you will see a full rainbow, but the light from the element samples will split into distinct lines, each of a specific frequency. Each line corresponds to a particular drop from a high energy level to a lower one. By analysing the frequencies observed, it is possible to directly measure the energy states within the atom, using the Planck-Einstein equation we saw before. Each element will have its own unique spectral signature, and this can be used to identify elements in an unknown sample. Scientists started analysing these spectra before we had any comprehension of the internal workings of an atom. Some of these lines appeared to be quite sharp. Others seem to be of principal importance in identifying elements. Some lines are a bit fuzzy or diffuse. Other lines were named as fundamental because, actually, I don't know the reason for this title. Sharp, principal, diffuse, and fundamental. These labels turned out to be not that useful, but the names stuck. And this is why the subshells of atoms are designated as S, P, D, and F. This is what happens in science when we nail down our nomenclature before we've established theory. We've covered a reasonable distance from the wave nature of subatomic particles through to the structure of atoms, the layout of the periodic table, and a simple experiment that allows us to glimpse something of the subatomic world. Of course, you really should do the experiment yourself. As promised, here are some slides that will enable you to get started. That's it for now. See you next time in the lab.